Hey, what's going on, guys? Let's look at this problem right here. Here we have two expressions are given. The first one is sum of product and the second one is product of sum. And the questions here asking implement using NAND gates only of any size. And the second one is asking implement using NOR gates only. The third one is asking implement using two input NAND gates. Okay, let's go for the first one. Implement using NAND gates only. So whenever they talk about NAND gates, first we have to write this one in terms of AND gate and then we can easily convert. So when they talk, like when we deal with AND or NAND, we always look at the sum of product. So sum of product, here we have WX, WZ and this one. Let's go ahead and draw this one in terms of AND gates first, then we can convert it. So in AND gate, we are going to, first one is, we have W and X going through an AND gate. So this is going to be W and X, and the next one is we have WZ entering a AND gate, and the third one is W bar X bar. So W bar and X bar entering a AND gate, and the next one is W, Y bar, Z bar. So here we have to have three input AND gate. Since they have mentioned use any of size, we can use three input AND gate, and then we can convert it into an NAND gate. Okay, so this is going to be W bar, and here we are going to have Y bar, and then here we are going to have Z bar, and all of them are entering OR gate because all of them are added together. So all these four are entering an OR gate. Okay, OR gate like this. Now our purpose is to bring everything in terms of NAND gate only. So to convert this one into NAND gate, what we can do is, if we put a NOT right here, this is mean NOT gate, but if I do that, I have to do the same thing here. So we are like if we put a NOT, we are complementing, but if we put another NOT right here, that complement is going to cancel. So it's going to be the same circuit we had before we do the complement. So this is not going to change anything. So we can do that here. This one and this one, and also this one. And also whenever you have complement, you can replace that one with this NAND gate. Like this is usually NOT gate. This W is connected to the NOT gate. It look like this, but the equivalent NAND gate for this NOT gate is this one. The two input of this one tied together and connected to the NOT, like connected to the NAND gate. So this is equivalent to this one. So we can do that one right here. But if you want to do that, yeah, like let's go ahead and do that one too. So first one, I'm going to throw everything in terms of NAND gate. So first one we are going to have is W NAND right here, and then here we have WZ going through the NAND gate, and the next one is we have W bar and X bar. So W going through the NOT gate. Instead of NOT gate, I can put this NAND gate right here. So it's going to look like this. Okay, and also X is going through the NAND gate, this NOT gate, so we can replace this NAND gate. And then here we have three things going through this NAND gate. So it's going to look like this. Okay, so three input through the NAND gate, and this is W, this is Y, and this is Z. All of them are going through this OR gate, but if you have OR gate like all of the NOT in front of this OR gate, that is equivalent to a NAND gate according to De Morgan's theorem. So we can replace this OR gate with the NAND gate. So finally we will end up with a circuit like this. So this is going to be the final circuit using NAND gates only. Now you can see everything is a NAND gate. Now let's look at the second ones. Implement using NOR gates only. So it's like same thing. Let's go ahead and do that. Let's get rid of this part. Using NOR gates only. So first I'm going to, when they talk about NOR gate, we are going to use the bottom one, product of sum. Let's draw the given one first, then we can convert it. Okay, so the given one is W bar X and Z entering a NOR gate, OR gate. This is OR gate because addition, entering an OR gate. So W bar and X and Z entering an OR gate, and also W X bar Y bar entering an OR gate. W X bar and Y bar entering an OR gate, and the next one is we have W X bar Z bar entering an OR gate, W X bar Z bar entering an OR gate, and all of them are ANDed together. So we are going to have these three connected to an AND gate like this. Okay, now the question here is implement using NOR gates only. So we can do the same thing like this before, like we can put a note right here. If we put a note right here and we had to put another note right here, so that's going to cancel each other. So we can do the same thing here, 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 and finally we will end up with this one. But also before we seen, when we have NOT gate, we can replace that one with a NAND gate, two input connected together. We can do the same thing for NOR gate. This is a NOR gate, and if you connect the input of this NOR gate together, that will also work exactly same as NOT gate. So we can replace this X bar Y bar, because X bar mean what? X is going through a NOT gate. So we can replace that NOT gate with a we can replace that one with a NOR gate also. NOR gate will look like this. Okay, so we can, it's gonna be same as this one. Like we are going to change this one using De Morgan's theorem. In De Morgan's theorem there are two equations. One of them is when you have all the NOT in front of OR gate, the equivalent is going to be a NAND gate, and also when you have all the NOT gate in front of AND gate, the equivalent is going to be a NOR gate. So these two are De Morgan's theorem. So we can transfer this one also using De Morgan's theorem, because this is going to be a NOR gate. Okay, so final circuit will look like this, and we know that we can replace all the X bar, Y bar, Z bar. Like instead of writing like this, we can put X, this one, and then that is entering through this one, similar to this one. But I'm gonna skip that step and just gonna draw the final circuit in with the expression of bar. Okay, in that way we can finish it earlier. Okay, so instead of X bar, I can put like X, this one, and then connected to this one, like same like that. But I'm just gonna put X bar, and then first one is W bar, and then X bar, and then Z. All of them are connected to the NOR gate, and then here we have W, X bar, and then Y bar connected to a NOR gate, and then the third one is we have this W and X bar and then Z bar connected to a NOR gate. So all three are connected like this. Finally all of them are connected to an AND gate. So that's going to be that can be replaced with a NOR gate like this. Okay, so this is going to be the final circuit. Now we are done with this part right here. The next thing is implement using 2 input NAND gates. Here we have created this one. Now this is our NAND gate circuit, but now they are asking to use only 2 input, because here we have 3 input. For this one we have 3 input, and also this one 4 input. So we have to find a way where we can change this one into a 2 input NAND gate. Now let's go ahead and try this one. Let's get rid of this. Okay, so first we had to figure out what's going to be the equivalent circuit for a 3 input NAND gate. How we can convert this one into a 2 input NAND gate. Let's see, some of you may think similar to something like this, like when you have a circuit like this, 3 input NAND gate, can we replace that one with a NAND gate connected like this? See, you may wonder whether it will work. Let's see. To find this one out, we can always use a truth table. So let's go ahead and create this one. So this is what, this is A, B, C whole bar, because NAND means whole bar. This is what A, B bar dot C whole bar, right? This is what this expression means. Now let's try this one through truth table. Since we have 3 variables, we are going to have 8 different combinations, because 2 power 3, that's going to be 8. So A, B, C, we are going to have 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, and the last one is going to be 0, 0, 0, 0, 1, 1, 1, 1. Okay, so these are the combination we are going to have, and then we had to see what's going to be these results. Okay, let's create let's get rid of this one. Okay, so here what we are going to do is, first we are going to see what's the truth table for ABC whole bar. ABC whole bar mean we are multiplying first, then we are taking the complement of that. So when you multiply, if you have 1 0, the whole thing is going to be 0. So wherever we have 0, that's going to be 0. Then if we complement that one, we are going to get a 1. So wherever we have 0, that's going to be 1. Wherever we have all of them 1, that's going to be 0. So this is 1, 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 this is 1. But for the final one, all of them are 1. So the product is going to be 1, like the AND gate is going to be 1. But if you complement that one, that's going to be 0. Okay, so this is for ABC. Now we are interested in finding out AB bar dot C whole bar, is it equal to this one? To find that one out, we can create another one, AB bar. AB bar mean what? AB multiplied and complemented. So whenever we have a 0, that's going to be 0, and if we complement, that's going to be 1. So until this one, we are going to get a 1. 1, 1, 1, 1, 1, 1, 1, and this is going to be 0, and the last one also going to be 0. And the last one we have to check is, we have to see C dot AB bar whole bar. C is this one, and we have to multiply that one with AB, and we have to complement at the end. So 0 times AB, that's going to be 0 times 1, that's going to be 0. 0 complement, that's going to be 1. Then 1, 1, that's going to be 1, that's complement 0. 0, 1, 0, complement 1. 1 times 1, 1, complement 0. 0 times 1, 0, complement 1. 1 times 1, 0. 1 times 1, complement 0. Then 0 times 0, complement 1. Then 1 times 0, 0, complement 1. Am I doing any mistake? It's look like I'm making some mistake right here. Okay, AB bar dot C. So 1 times 1 complement, that's going to be 0. It's right, this is correct. Okay, so here you can see this is not the same. These two are not the same. Not the same. It means what? this will not work. We cannot replace like this. So we have to find another way to replace this 3 input circuit. So we found out this one doesn't work. Let's try some other things. Okay, so let's see what we can do. So here we have 3 input circuit, 3 input like that, let's say A, B, C, and that is NAND gate, right? 3 input to the NAND gate. Now instead of writing like this, we can also write this one as 3 input 3 input like that, A, B, C. Instead of this NOT, you can put a NAND gate 2 input tied together as we seen before. This NOT mean it's a NOT gate. It's similar to this one. So we can do that, right? Instead of writing like that, we can do that one right here. Now let's see how it's gonna help us. So first we have brought this one like this, and then what I'm gonna do, I can bring this C to this one. You will see why, like A, B, and if I split this part and connect the C right here, okay, and this is an NAND, okay, this is like this, and connect it like that, and it goes like that, right? So this is same as this one, AB. This one is what? ABC complemented at the end. This is what? AB dot C complemented. It's same thing, right? Same expression, we can draw it in a different way. Now we want all of them to be 2 input NAND gates. So we had to change this one into a NAND gate. The easy way is, if we put a NOT right here, we had to put another NOT to cancel that one. But by doing so, I am changing this one into a NAND gate. So now I change this one into a NAND gate. Okay. And also instead of this instead of this NOT right here, this is a NOT gate, right? So I can also, if I want, I can also convert this one into a NAND gate by replacing a NOT gate like this. So the final circuit we can have is like this. Connected to a 2 input NAND gate like this. Okay. So this is going to be the equivalent circuit for this one. So when we have 3 input circuit, we can replace that one with this one. So let's go ahead and do that for this one. So here we have to have X, Y, and for Z, I'm going to turn this one into like this. Okay. So let's get rid of this one first. First, let's see how it's going to look like. So A, B. So these two are going to remain the same. Okay, let's go ahead and do the replacement. Let's get rid of this part. Now we are going to replace with 2 input NAND gate. So it was 3 input and all of them were connected to a NAND gate, a bar. Like this one was W, the last one was W, X bar, C bar. It was W bar, X bar, C bar, right? It was a W bar, X bar, W. Oh, I'm looking at this one. It was W, Y bar, Z bar. I'm looking at AND gate, right? Not OR gate. AND gate. So this one was the last one. Now we are going to replace this one with a 2 input circuit. So W bar going here. You can do the same thing, like W entering this NAND gate. So you can do that one. And now to shortcut, I'm just writing like this: W bar, Y bar, and then we found the equivalent circuit like this, connected like this. At the end we have something like this, and then here we have the Z bar connected. So this is equivalent to that 3 input circuit. Now we have converted this 3 input circuit into 3 input NAND gate into 2 input NAND gate. Now we have to see how we can convert this 4 input NAND gate into a 2 input NAND gate. Now let's see. So when we have a 4 input, let's get rid of this one. Now we are going to see how to convert a 4 input gate into 2 input NAND gate. Okay, so first we have a 4 input NAND gate, 3, 4, and we are going to see how we are going to convert. Okay, 4 input mean like this one. Instead of this one, we can write it like same as we did before. Instead of this note right here, we can replace that one with a NAND gate, 2 input connected together. So it's going to look like this. Okay, so this is A, this is B, this is C, this is D, and at the end here we are going to have what? To change this one into a NAND gate, we can put NOT right here and here, and NOT here mean this NOT we can replace that one with a NAND gate, 2 input connected together like this. So this gonna cancel each other. In that way we don't change anything. It's gonna be the same as the one without nodes. Okay, so now we have converted this one into 2 input NAND gates. Here you can see all of them are 2 input NAND gates. So this one I can replace that one with a 2 input NAND gate. Let's get rid of this one and do the replacement. Okay, so here we have this one connected to a NAND gate, and this one connected to a NAND gate like this, and after that this is going through 2 input connected NAND gate, 2 input connected NAND gate, and at the end all of them are going through this NAND gate right here. So that's going to be the final circuit, and that's it. That's how we convert 4 input 3 input circuit into 2 input NAND gate circuit. I hope this helps. Thanks for watching.